MCQ question number 22. In this question, a plane electromagnetic wave is given to us which is propagating in a lossless dielectric. The electric field in this region is given by E equals to E naught x cap plus A z cap exponential of iota k naught bracket minus ct plus bracket x plus root 3z. All the brackets are closed. Now, in this expression, we can see that c is the speed of light in vacuum, E naught, A and K naught are constants, and x cap and z cap are unit vectors along x and z axis. We have been asked to calculate the relative dielectric constant of the medium, that is ER, and the constant A. Now, we know that the electromagnetic wave is always transverse in nature. So, the wave vector and the electric field vector, if we apply an operation of k dot E, that should be equal to 0 because these two are always perpendicular in nature. If we put the expression of these two vectors, we will get the value of A, that is equal to minus 1 by root 3. Now, we also know that in electromagnetic waves, phase velocity, that is V, is equal to omega by k, where k is the wave vector. If we put again the value of k vector, that is k naught x cap plus root 3 z cap, we will get V equals to k naught c by 2 k naught, or finally phase velocity V equals to c by 2. We also know a relation for the refractive index, that is n equals to c by v. Now, if we put the value of c and v as calculated earlier, we will get refractive index in this scenario equals to 2. And if we know the refractive index in a particular medium, we can also find the relative dielectric constant in that medium, because a refractive index is equal to root of relative dielectric constant. So if we have to calculate the relative dielectric constant, that is ER, it can be calculated by squaring the refractive index. So the relative dielectric constant of the medium will be equal to 2 squared, that is 4. So the correct option for us in this question will be option A. MCQ question number 29. In this question, a simple cubic structure of lattice constant A is given to us. One plane among a set of parallel planes intercepts x, y and z axis at 2a, a and a respectively. The interplanar spacing is what we have been asked to calculate. Now, as we can see that intercepts is given to us as 2a, a and a. If we have to calculate Miller indices from these intercepts, the steps are: first we have to divide them by lattice constant, so we will get 2, 1 and 1. Then the next step will be that we take the reciprocal of this, so the final expression that we will get is 1 by 2, 1 and 1. Then we have to calculate the Miller indices by clearing the fractions. So we will multiply it by 2 and the Miller indices that we will get will be 1, 2, 2. If we have to calculate the interplaning spacing, it will be something like d equals to a upon root of h square plus k square plus l square. The value of h, k and l we have just calculated as 1, 2 and 2. So if we put these expression of the values of h, k and l, we will get d equals to a by 3, that is option D is the correct answer in this question. MCQ question number 30. In this question, we have been given a doped semiconductor having the electron and hole mobilities of mu n and mu p respectively. Its intrinsic carrier density is given to us as Ni, and we have been asked to calculate the hole concentration P, for which the conductivity is minimum at a given temperature. Now, we know the expression for conductivity is sigma equals to Ne mu n plus Pe mu p, and one more relation, we know that the intrinsic carrier density, that is Ni square is equal to N into P. So if we have to replace the value of N, that is the concentration of electron, in terms of the given quantities, that is intrinsic and hole densities, we can put N equals to Ni square by P. So the expression for conductivity that we are having is sigma equals to Ni square E mu N by P plus Pe mu P. Now our question was that we have to find the hole concentration for which the conductivity is minimum. So to find the minimum conductivity, we just differentiate the expression of conductivity in terms of P. That is d sigma by dP is what we will calculate, and it will be coming as minus Ni square E mu N by P square plus E into mu P. Now if we have to calculate the minimum conductivity, we will just equate d sigma by dP equals to 0. And if we do this, we can easily see that the value of P will be equal to Ni root of mu N by mu P from the expression d sigma by dP. So the correct option for us will be option A.
MSQ question number 35. In this question, a particle is moving in two-dimensional potential well of a potential V of xy equals to 0 from the x from 0 to L and y from 0 to 3L and infinite elsewhere. In this question, we have to find out the correct statements corresponding to ground state energy E1 and ground state eigenfunction phi naught. So first of all, we know that in two-dimensional box, the energy eigenvalue En equals to pi square h cut square divided by 2m in bracket nx square upon a square plus ny square upon b square, where nx number of modes along to x-axis, ny number of modes along to y-axis, a is length of dimensional box along to x-axis, and b is length along to y-axis. So for the ground state, nx equals to ny equals to 1. So ground state energy E1 equals to pi square h cut square divided by 2m 1 by L square plus 1 by 9L square, that is equals to 5 pi square h cut square divided by 9mL square, where the length of the box along to x-axis is L and along to y-axis is 3L. Similarly, the eigenfunction ground state eigenfunction psi naught equals to a sin nx pi x upon L into sin ny pi y upon 3L, where nx and ny equals to 1. So for normalization, the cat-bra product of this wave function should be equals to 1, or psi star psi should be equals to 1. So cat-bra product of psi naught equals to a square integration from 0 to L and 0 to 3L sin square pi x by L sin square pi y by 3L, that is equals to a square 3L by 2 into L by 2, that should be equals to 1. That implies a is equals to square root of 4 upon 3L square. So the ground state wave function psi naught equals to square root of 4 divided by 3L square sin pi x by L sin pi y by 3L.
MSQ question number 38. In this question, we have been given a region of space in which there are uniform electric and magnetic fields which are mutually parallel. Now a charged particle released from rest in this region, and we have been asked to calculate which paths are impossible for this particle. Now, as we can see that the charge is released from rest, so the electric field will accelerate the charge in the direction of itself. Now, if the charge starts moving because of the electric field, the velocity of charge will be parallel to the electric field, and so it will also be parallel to the magnetic field, because the electric field and magnetic field are given parallel to each other. If we have to calculate the magnetic force on this charge, we can calculate this force by the Lorentz equation, that is Fp equals to Q, that is charge, into V cross B, and the magnetic force in this particular scenario will be equal to 0, because V cross B will be 0 as V and B are parallel to each other. So the only force acting on this charged particle will be the electric force, and it will move the charge in a straight line. So the impossible paths that we were asked to tell will be circle, helix and cycloid. So the options correct in this question will be option B, C and D.